we've gotten through discussing the dust, so now let's move in and talking about the gas. And here's I love these pictures. You're going to have examples of a star. This is a newborn star, was formerly a protostar, and it's got this jet, this geyser of gas and dust flowing off of it. So we're going to start making a connection to the temperature of the gases, their density, and their relationship to the star or whatever got them at that temperature. All right. So let's got a couple of related terms to fill in here. So I tried to color code these to distinguish between them, and I'll have some pictures in the next few slides to help fill in the void of what I mean by these different terms. So let's start bigger. All right. We're going to have our interstellar gas, and that is kind of just a blanket catch-all term. This is the gas and dust between the stars, similar to interstellar medium. When we say medium, we're talking about everything in there, including sometimes radiation. If I focus down into gas, I'm going to focus on the gas between the stars. Then we talk about interstellar clouds. And by interstellar clouds, we're going to say these are quote-unquote high densities. Right? There is a larger concentration of atoms there. Right? Nebulas are going to be good examples of these types of clouds. Right? So you're going to have high density regions of interstellar space. And then the remaining bits, whatever's not inside the interstellar clouds, is what we call the intercloud gas. So interstellar gas, take of all of the space and say, what's all the gas there? Now, interstellar cloud, think of a concentration. There is a pocket of gas here, right? There's a big cloud, and that cloud moves around through the cosmos. So, big picture, interstellar gas, a cloud, that's our interstellar cloud, and then everything in between the clouds, is going to be our intercloud gas. So this is the big catch-all, and then we're narrowing down smaller and smaller concentrations. So let's start comparing some of these properties. If I have, say, a hot intercloud, right? If I have a hot intercloud, we're going to talk about temperatures of upwards of 1,000,000 Kelvin. So this is the stuff between the clouds. It's going to be very hot, very low density. There is not a lot of atoms here, but the ones that are there, they're whipping around very rapidly. So these, you can think of stuff that got ejected off the star or maybe propelled through the cosmos by like a supernova, and they're just flying through the cosmos. All right. We're going to go down in temperature. This table is grouping them in terms of temperature. If we get to what, say, is a warm intercloud gas, so we're not inside nebulas, which is just the warmer material. The density's gone up. There's a bit more of these warmer clouds, and they've cooled off. They're closer to about 8,000 Kelvin. Still running around rapidly. And keep going. You've got the colder gases, the density's going up. Notice the relationship. The faster, or specifically the hotter the particles, the lower the density. That's a key relationship. Right? If you're really hot and flying around, remember, these clouds don't have any sort of gravitational body really to hold them in place. So as they just disperse because of their rapid motion, the faster you move, the quicker you get away from each other. All right, great question. Does the cloud float freely, or is it orbiting something? These clouds are not orbiting anything specifically. They're just out there in the cosmos, and they'll have motions where they're slowly expanding in size or sometimes collapsing down. And the motion of these clouds, you kind of can think of them as like clouds in our atmosphere, how just the random winds push these clouds around. Well, here on Earth, the winds are due to changes in pressure. Out in the cosmos, the stellar winds? Well, that's due to, saying, stars ejecting material or supernova pushing things out. And so, yes, these are clouds that are basically free floating. They're not bounded to anything. What we'll find is that these clouds are thousands of times bigger than any stars, and there'll be houses for stars to start forming inside them. So, let's come down here. About half of all the interstellar gas is trapped in the clouds. And that's what I mean about, like, these clouds are going to be star birthing regions, right? And the clouds themselves, about 2% of space. So remember, big vacuum, big void of emptiness, and then pockets of higher density, right? So half the gas in the cosmos are in these clouds. Those clouds are concentrated into tiny space, so the rest of that big void is that intercloud gas. Think of the hotter, rapidly moving stuff. So, some pictures to try and help us with these terminologies, trying to narrow these down. Here's a great example of an interstellar cloud. This is a Cephas b. It's called a molecular cloud. That thing's only a few thousand light years away from Earth, so it's definitely in the Milky Way. This is something you're going to start noticing. Is we're going to start distinguishing, are these things that we're seeing inside our Milky Way or outside? And most of the grandiose pictures we see, they're going to be inside our Milky Way. So here's a cloud, and you literally can start seeing regions of, this is not a star behind the cloud, it's a star inside it. So these clouds are these massive enveloping things that are just floating through space. Then we have things like the Intercloud Gas. So this is, once again, looking at the full range of the Milky Way, and we're just seeing the wide range of gas that's just glowing, right? And in the next few slides, we'll start talking about what's the source of their glow, and specifically what wavelengths of light they tend to glow in, or what temperature they're at. So, go back a bit. Interstellar cloud. These are technically denser regions of space, but this can still be hundreds of light years in size. You can find pockets of even denser regions inside the cloud. Now, get outside those clouds, and there you'll have the intercloud gas, which is just the gas spread throughout the Milky Way. All right. So let's have an example of talking about just the intercloud gas, right? We can still find a wide range of temperatures. Remember, these things can be hundreds of light years across in size. So that means that their temperature can be wildly changed. We could have something like a supernova explosions. Supernova, for our purposes, is just going to be a big massive star collapsing and just blowing up. And I do promise we will talk about that in more detail. But for now, we'll just say big star went kaboom. And when it does, that heats up a lot of the gas in that region. Gives them a lot of thermal energy, and specifically kinetic energy, to just fly through the cosmos. So you can have very hot regions, right? We can also have regions that are star forming. So big giant gas cloud. If you want to continue the analogy we started earlier, clouds floating through our atmosphere, and it's forming raindrops to pour down on us. You can think of it as similar. There's the intercloud floating through space, and inside that cloud, there will be regions where things are condensing down enough to start forming stars. So, wide range temperatures and wide range of regions of what is producing the dominant glow at these regions of these clouds. We can have ionized gases. And an ionized gas, what we're mostly saying is hydrogen with no electrons. That's going to be the bulk of what we're talking about. Hydrogen with no electrons, so just this charged particle floating around. And these things are going to be upwards of that million of Kelvin. Cool down a little bit, get away from the big explosions, and you're going to find sometimes a lot more neutral gases. And that's where they tend to glow at around 8,000 Kelvin. And the spectrum of light is going to be this H alpha line. I'm going to go over this in more detail. What the heck does this H alpha line mean is? But the emphasis I'll say now is that H alpha tells us how we know that there's a lot of neutral gas in the cosmos. And then keep going, you can find things like molecular gases. This is going to be gases, a bunch of atoms sticking together. They're going to radiate in a bit more of the long radio waves. Remember, like the meter-long wavelengths, right? And what's producing this spectrum of light we see is going to come from what we say spin flips. So I'm going to go through these in a bit more detail. All right, it's just not good enough to have the text there. So, breaking that down, let's have our hot gas. And this is a picture we had at the very beginning of this section. We said, look, we live in a bubble of X-ray gas, right? Upwards to millions of Kelvin floating around. So these are high energy charged particles flying around, and they're naturally giving off X-rays because of how fast they're moving. So we look across in an X-ray spectrum of the Milky Way, and we see tons of X-rays. And you're also going to see some brighter spots, right? Those bright spots are most likely what we'd say recent supernova. Recent is a cosmological timescale, so we're saying thousands or tens of thousands of years recent. But either way, recent in the sense that a star blew up, and when that happens, an insane amount of energy gets violently released. And so we'll find these brighter spots in the Milky Way of X-ray radiation from the big violent explosions. And that produces the hottest gases that we see out there. Now we cool off a little bit, right? Now we're going to start seeing things like pictures like this. We're going to see a lot of red and a lot of glowing spots, right? So the red, that's going to be the stuff that's in terms of about 8,000 Kelvin. And this red literally comes from what we say, this is the H alpha line. So what the heck is the H alpha line? This is an old chemistry term, in essence. Spectroscopy term. So some of you might remember, we've talked about this before, the Balmer series. These 4 lines here, this is chemically identifying hydrogen. You're looking at the atomic properties, and that's what this picture is. Here's your hydrogen atom, 1 proton, 1 electron orbiting around it. And we say, what energy shell is that electron in? And for this line specifically, this wavelength of light, it gets produced when an electron starts at this energy shell, the n equals 3. So remember the bookshelf analogy. You start off, right? If you start off at a high shelf and you drop to a lower shelf, you start high, go low, you spit out a photon. And so by spitting out a photon, this span here, the H alpha line, corresponds to this reddish glow. So when we see the Milky Way, this is part of how we know most of the universe is hydrogen, is that we see almost entirely hydrogen lines. Now the brighter parts, you'll notice they're a bit more concentrated towards the galactic center, concentrated where there's a lot more stuff flying around. So this is what we call an H2 region, and that's just a older term to say ionized hydrogen without electrons on it. And so the gas here is going to be a little bit hotter as it's flying around potentially more stars that are being crushed down in more stars. All right. Finally, we'll reach the coolest of the gases. All right, we're going to keep cooling down. And you start to see the longer wavelengths. Think back to the last part. Whereas we extended the wavelength of light we see, if we make the wavelength longer, we get to see more and more material. So we cool down. We get into what's called the H1 region. H1, proton with an electron bounded to it. That's all we need to know. It's proton with an electron bounded to it. These are going to be cooler gas molecules, and they're going to be radiating in this wavelength of 21 centimeter line. And this comes from what's called an electron spin flip. Right. The example we like to say is take an object, spin it around. Right. This is a classical analogy. It doesn't work correctly for this. But I can say I have this pin spinning around and say, well, what's the rotation of this one? And then if they sync up, if I ever not drop them, I can say, do they sync up, or are they opposite directions? So they're rotating in unison. I do not have the dexterity for this. They can rotate in unison or opposite each other. All right, that's our classical way to think of atomic and electronic spin. So you can say, look, the spin of the nucleus versus spin of the electron, and they'll flip. They could be in unison, or they could flip around. And that result of this electron, of those electrons spinning around, that spits out a photon. It's a very low energy photon, which is why it has such a long wavelength, 21 centimeters. You're talking about a wavelength of, honestly, not much, a little bit shorter than the length of my paper here. A wavelength that goes probably about about that length is what the wavelength of the light coming off from this spin flip. So it is very much a cooler spectrum. I'm going to not respond to the silly jokes, but I do appreciate them. So, the electrons are cooler, and it's the spin flips that are causing them to radiate these long wavelengths. All right. So, quick reminder, right? I'm looking out in the cosmos, and say there is a star and then a cloud of dust between us. What happens to the light of that star? We've talked about this before. Do you guys remember? All right. So first answer I see was a redder from the Doppler shift. And gotta be specific here. It is not redder from a Doppler shift. Doppler shift is going to be a different, but close. All right. So what happens is, what that gas cloud does is it tends to block a lot of the visible light, especially a lot of the ultraviolet waves, and it tends to glow in the infrared. So yes, the light tends to be redder, but it's not a Doppler shift. Doppler shift is due to the motion of the star towards or away from us. This is going to be a shifting of the colors because something's blocking it and then getting heated up. So let's have a picture of this, right? We're going to have what we call these molecular clouds. We'll have these molecular clouds. So you're going to have stars across the spectrum, and then we're going to see just these dark voids. And these dark voids are not going to be black holes. That's a common misconception that this is a black hole. No. This is just a cloud of dust between our view of the stars behind the clouds. So it's darker because it's blocking a lot of the visible light. All right, so a question that comes in. Is it because the red color has less frequency and a longer wavelength? Correct. The longer the wavelength, the lower the frequency, the higher the probability of it being able to pass through the material, in essence. And that's why we tend to see a redder color. So, when we see dark bands like this, we'll have another picture and we'll fill in the red colors that are missing. All right. So, this is a big molecular cloud. A lot of hydrogen. And another question. Do the clouds not reflect light? They reflect some amount. And if they reflect that light, then it's very unlikely to be reflected, bounced towards our eyes. Remember, we're talking about grains that, like, even this is orders of magnitude too big. These grains are at max 300 nanometers, so they're going to be tiny. All right. So let's look at this picture with infrared stick glued on top of that. And there you can start to see the stars hidden behind. So often question, how can we tell these apart from black holes? Well, it's a little tricky, but one of the biggest answers is that these black voids are significantly easier to spot than black holes. It's because that this thing is blocking a huge range of light. So the cloud itself is very close to us relatively to the stars. So this cloud is very close, which means it has a huge angular size. Think back to when we talked about the angular size of the moon versus the sun. The closer something is, the bigger angularly it is. So these glass clouds have a huge angular size, which makes them much easier to spot. Whereas the black holes in the universe, they're going to be a lot further away from us. And so we are less likely to be able to see them. And on top of that, these molecular clouds are going to be gigantic. Black hole will be a couple of times bigger than our sun in terms of its horizon. This cloud could be hundreds to thousands of light years in diameter. And so the cloud itself is just significantly bigger than a black hole. So what we've done here is stitched on looking at this molecular cloud with an infrared spectrum. And we get to see all the stars that are basically behind it. And doing some tricks with some radio waves, we can figure out some properties of these clouds. And they're very cold. They're on average around just 10 Kelvin. But there's still a lot of mass in there. This one in particular is about 107 solar masses. And size here to here in this picture is 120 light years. An event horizon is going to be smaller than a light year. And that comes back to the previous question of why are these easier to spot than black holes? They're significantly bigger.